My name is Doug Littrell. I live in Kansas City. Today is May 23rd, 2017. I've been conducting some tests of the equivalence principle. The first test I conducted was about a week ago. It employed two 48-inch, 4-inch diameter clear plastic tubes capped at the bottom, fastened to a wall, filled with water. Two identical plastic spheres that were hollow, about the size of ping pong balls, were drilled so that lead pellets were added, enough in one so that it had a mass of 30 grams, the other one 31 grams. The holes were taped shut, then those were dropped simultaneously in one in each tube of water. And the less massive ball, plastic ball, was about a foot from the bottom of its tube when the more massive ball struck the bottom of its tube. The reason I believe that impacts whether the equivalence principle is valid concerns resistance of a medium. If you can have two identical shaped, vertically spherical objects that have different densities dropped in relation to a gravity source like the Earth, you're essentially eliminating that resistance from the equation because it's equal. It's equal on both bodies, so that the only thing you're observing is the attraction or pull force of gravity on the heavier or the greater mass object. This is borne out by the common sense of a 150-pound man pressing down on the surface of the Earth on his feet less than a 250-pound man presses down on the surface of the Earth due to gravity. Gravity is a rectilinear attraction force. Orbital mechanics operate in relation to that rectilinear force, not due to curvature of space or space-time. Before we get into the second test, I'll go ahead and explain a little bit about orbits. Whether a body is coalesced next to its star or is an interloper that was captured, wander off because the white dwarf can no longer hold its planets that it previously held, let's say. Or, let's say, planets and moons that collided and broke into pieces of rock and ice of various makeup. Some of those pieces wandered, let's say, toward our solar system, toward our star, and were captured. Okay, now if they're captured, this happens essentially where in the location of what the orbit will essentially have, where it has its perihelion, its closest distance to its primary, which is the sun in this case. As it flies by, if it doesn't have enough mass for its distance, or if it has too much velocity, it will not be captured. It will fly off in a parabolic track. And much like, let's say, gravity assist used by scientists who understand how that works and use a planet in relation to a spacecraft to give their spacecraft more velocity by that craft falling toward it, but not directly toward it enough so that it's captured and begins to orbit. So it gains velocity by falling somewhat toward it, then it turns a little bit in a parabolic track and it gains velocity and moves on in the direction that they want it to, because they're very talented at doing that, figuring that out. Now, when a planet or an asteroid or a comet, let's say, is captured by the sun, generally it's an elliptical orbit, and it's, as it moves away from its perihelion in its elongated course, it's moving essentially away from the star. This rectilinear attraction force of gravity begins to slow the object, the body that's moving away. It's not moving directly away, but it's moving away, and it loses velocity. And then when it reaches its aphelion, its furthest distance from the star, that's when it's moving at its in its orbital path at its slowest velocity. And then when it passes its aphelion, its farthest distance from the sun, it begins to curl by attraction toward the sun back and come more toward the sun. When it does, it starts to accelerate and gain velocity. None of that has anything to do with the curvature of space or space-time. All of this can be explained by attraction force, which hopefully these experiments will help demonstrate. This experiment uses 6 electrical conduits, steel, that have been fastened parallel to one another, and these are 9 feet long. They terminate into this rolled up carpet, inside of which there's a concrete block. Now, several factors can skew the conclusions that might be drawn from this test. One of those is the gate mechanism that releases 2 balls. Those centers up or back until the gate falls. To help the gate fall quickly and get out of the way of the balls, a bungee cord has been attached to these milk crates and to the loop of the wire that's part of the gate. A rubber band has been strapped to the hook of the bungee cord and the part of the gate, so that when it's cut, the gate will not be a factor to skew one ball rolling faster than another. So that mechanism is to remove that gate from being a factor in how fast either ball rolls down the track. Another factor, first of all, we're going to use 7 balls, 5 of which are foam rubber, except for these 2 are hollow rubber balls. This one's unpainted. This is the smoothest surface ball. Surface smoothness is critical to how fast the balls roll down the track as well. This one has been painted, spray painted black. It's a little less quick moving down the track than the unpainted ball, hollow ball. But they essentially have the same mass except for the added paint. But they roll essentially the same, as it turns out. These are green spray painted balls. They're foam rubber. The A ball is a little different foam rubber than the B ball. The A ball is a little denser foam rubber, and its mass is about a half a gram more than the B ball. There are 2 lead balls that are going to be used. One's 3 pounds, one's 10 pounds. These have the roughest surface, so this is a disadvantage to those having the greatest speed, because particularly This one you can see when it was molded, it didn't come out as perfect as I would have liked it to. But this one, the 10-pound ball, has really gotten beat up with these tests. I've been doing these tests, this particular test, over and over for several days, and the surface is pretty beat up. It was done mainly over a concrete surface, and the ball being very heavy and massive would sometimes jump over what I had placed at the end of the track to stop it, and it would hit the concrete and dent it a little bit, make it rougher. This has happened many times, and this is the rougher ball. Now, they've been painted with a metallic paint to help compensate for the added roughness, but they are smooth enough to conduct this test at this time. They can get rough enough that they slow too much. This ball is another foam rubber ball on its interior. It's got a nice smooth skin. It's perhaps the least massive of all these balls, even though it's the same diameter as the larger lead ball. Exactly. All 5 of these balls are exactly the same diameter as well. Another factor besides surface smoothness and the gate, which we've discussed, that can skew the results of this test is whether one track is faster than another. And to test that, we'll start with the 2 foam rubber balls, painted foam rubber balls. We'll run the slightly more massive A ball, which is about a half a gram more massive than the B ball, down the number 1 lane, or number 3 lane, pardon me. This is number 1 lane, this is number 3 lane. And the number 3 lane looks like it might be a little faster than the number 1 lane. Let's reverse the balls and try it again. Now the A ball is in the number 1 lane, the B ball in the number 3 lane. Look like they hit almost simultaneously. So I really wouldn't expect a half a gram of difference to make any significant difference in the speed they roll down the track. I would say that the indication is that the number 3 lane is a little faster than the number 1 lane. To double check that, let's use these 2 essentially equal mass balls. One unpainted, the unpainted one will roll faster than the painted one. The painted one the paint was applied unevenly, so it's a little bit slower because it has a rougher surface. Let's roll these to double check for lane, the speed of the lanes. One being